This is a very exciting project. I will talk today about eRHIC and how we went through many concepts and many crises. In this presentation, I will touch only a very few of these unique crises and some solutions that we found to them. And I really want to apologize to my colleagues from eRHIC team that I cannot cover all twists and turns that we went through. So it's so my talk related to following that everybody here knows that there is RHIC exists at 3.8 kilometer circumference tunnel dominating Brookhaven landscape with two superconducting accelerators crisscrossing each other 6 times around the circumferences where two detectors are located, star and Phoenix. So my talk will be about adding to this already very versatile machine, electron machine in the same channel to add leptons or electrons and maybe even positrons in the future to the capabilities of this facility. So before engulfing into depths of my presentation, I would like to inject some thoughts why we need colliders. So many people are fascinated about modern electronics, ever smaller and ever smarter phones and flat TVs. But Hurricane Sandy probably reminded us, it was a very crude reminder to many of us, how miserable life would be with electric power. So all this part we really needed. And can you imagine that just 200 years ago, electricity and magnetism were actually on the forefront of fundamental physics, and taxpayers were mostly aware about electricity by the fact that their neighbors or somebody in their town were killed by lightning. So it was more evil force than anything useful. And that 180 years ago, as a part of his fundamental research, Michael Faraday discovered a connection between electricity and magnetism, which turned out world around because it's become a foundation for electromagnetic generators. So, if 200 years ago, instead of, is it working? If 200 years ago, instead of investing in fundamental science, financial minister of Great Britain would decide to invest it in some very, very fancy, at that time, engineering gadgets like steam engine, or maybe into more bayonets and horses, it will be very, very different world that we are living today. So what I want to remind before starting my lecture that there is a very, very big value of fundamental science, and I think it was really emphasized very well by Michael Faraday when he was replying to Minister of Finance of Great Britain and future Prime Minister Gladstone, who asked him about essentially why the hell you are doing this with useless, studying this useless electricity, that he told that one day, so you may tax it. So we shouldn't forget and remind ourselves and our politicians that fundamental science actually is probably the most profitable investment the society can do to develop itself. So I can further expand on saying that, of course, since Greek philosophy, people were looking into the world around us, looking into the stars and trying to understand what they're built from, how it all started. And it's amazing that how RHIC and eRHIC in the future could rewind time backwards and before stars were born and to look into the matter just initial bursts occur. So they can work as a high-resolution femtoscopes to look inside small particles, as well as, on the other hand, reveal the nature of the larger stars. So both RHIC and eRHIC, as other colliders, are not about colliding particles for the heck of it. They're here just to understand the fundamentals, laws of nature called quantum chromodynamics of QCD, which is responsible for the all visible matter in the universe. So looking deeper inside the nucleus, so since Greek philosophers, time of Greek philosophers, we learned a bit, Athena too, so we learned that there's actually atoms which consist of very tiny speck of nuclei and electrons which are circulating around them. We also learned that nucleus consists of neutrons and protons. Protons, in turn, consist of quarks and gluons. And, wow, this is real trick. This was supposed to stay in back and in other direction. It's happening. I always blame inventor of PC for doing this to me, but it's okay. So essentially, the idea is that we're going deeper and deeper and into femta region. So you can see essentially here we have scale about 10,000 and additional factor 1,000 go to the quark and gluons to the femtometer scale. To some degree, it's a similar scale as you're going from map of United States than to see individual buildings and in Manhattan. So, but the story doesn't end here. As I mentioned, proton and neutrons consist of 3 quarks, which connected by gluons. Proton consists of 2 up quarks and 1 down quark, and neutron 2 down quarks and 1 up quark. So, but as I mentioned, that neutrons okay, just a second. That quarks are surrounded by conglomerate of gluons and C quarks and antiquarks. And what is very interesting is that electrons actually carry have a very, very low mass, and nucleons, protons, are about 2,000 times heavier, which means that nucleus of atom carries from 95% to 99.8% of the mass. And this is not the end of the fun, because if you go further and further, what you will find that actually quarks inside proton or neutron actually carry a very, very small portion of mass, only about 1%. The rest of the mass is generated by gluons. So this is quite interesting if you think about it. All visible universe around us is surrounded by 99% of glue, about 1% of quarks, and 2,000% or 200% of electrons. So, as I mentioned, we are completely dominated by gluons. So this is a really complicated soup. And this is something which is quite unique for particles which are called hadrons. Hadrons essentially are not point particles, not elementary particles. They consist of some conglomerate of or distribution of various particles. And this is shown in real scale distribution of quarks and gluons and strange quarks. C quarks as a function of so-called Bjorken X. This is actually part of momentum carried. It means part of the energy carried by these particles. You can see that quarks really contribute very little, while gluons definitely dominate the picture. But one of the also very interesting things that essentially the density of them growing, and somewhere it will be saturated. And in a short, I just want to remind everybody that we are what we are made for. So the other thing that one thing which is worth mentioning that gluons are probably close associates of photons, which are carriers of electromagnetic force. But in the contrast with electromagnetic force, which is falling as far as the distance, force of the strong force remains constant, which is essentially like a rubber band which extending. And this is something which is really different from photons. And also one important feature is that gluons, in contrast with photons, interact with each other in the absence of quark, which means that intrinsically quantum chromodynamics is completely nonlinear and also very, very complicated things. So now I'm switched to accelerator science, and before repeating again a few buzzwords such as luminosity, cooling, and ARL, I will mention what the meaning of them. Sorry for the simple formulas for people who are really familiar with it. So one important feature is that if you think about why luminosity is important, because if some experiment is looking for producing some events, for example, new particles or some decays, whatever they're interested in it, so speed with which they will be produced will be proportional to cross-section of this process multiplied by luminosity of collider. So collider is where luminosity is essentially the key element of any collider, which means that, for example, if we increase luminosity tenfold, then experimental physicists will collect amount of information in 1A, collecting decade worth of information, and can do something new with this machine. So it's a very, very important feature, and it's described by a very, I will say, deceivingly simple formula. Deceivingly because there is a lot of hidden stuff in it. So number one, there is it's product of collision frequency of the bunches and population of two bunches which are colliding, N1 and N2. So one thing, and then it's divided by cross-section area in location of the collision. So one thing people can think, well, why not to increase these numbers by a factor of 10? It turned out that you will run into some kind of instability or limitation, a practical limitation, for example, ion clouds in RHIC. The other possibilities will be to reduce cross-section of this area. And for round beams, which are typical for RHIC and eRHIC, this is just a simple product of beta star. Beta star is a envelope of the beam in a collision point, essentially distance at which area of the beam increases by a factor of 2. And emittance. Emittance is nothing else than phase space volume, transverse space, phase space volume occupied by the particles. So beta star, one of the things people can think about, well, we can reduce beta star to, let's say, to 0 and go through the roof. There is limitation, and one of the most fundamental limitation will be acceptance of your accelerator, or most likely dynamic aperture acceptance. So the other way of doing it is to reduce emittance. And emittance, as I mentioned, this is just a phase space volume occupied by a ensemble of particles. In geometrical sense, this is just, for example, transverse position and a transverse angle of the particles. From Liouville's theorem, if people remember still classical mechanics, we know that non-dissipative systems do not preserve presume phase space volume, so very linear dissipation. And unfortunately, there is no natural dissipation process like for electrons, for example, which are leptons or point particles. For hadrons, because they do not radiate any significant portion of their energy, it means that phase space volume stays the same, emittance stays the same, so we really need to introduce cooling. And I will touch upon a couple techniques that we use in accelerator physics to do this. Okay, and finally, what is eRHIC? And eRHIC is actually a very interesting idea which was suggested quite long ago by Maritigna from Cornell University, and it's perpetuum mobile of the accelerators, especially when you use superconducting RF LINAC. So the idea is that you inject beam at very low energy, then you accelerate as many times as you need, use the beam, and after that you change the phase, because this is linear accelerator. In the linear accelerator, accelerating voltage or energy gain is alternating function, just sine function of the time. And so when you accelerate, you are sitting on the top of acceleration voltage by doing circumference of this path, the time equal integer number of these periods. And what you're doing here, you add additional 180 degrees. And after that, instead of acceleration, particles going through the same process, but in decelerating voltage. And by doing this, you return energy inside superconducting linear accelerator cavity. So, and the other beam will take it out. And so essentially it's becoming a lossless mechanism. You dropped only very, very small energy. So by doing this, you can really recover 99.9% of the energy. And I will demonstrate this on the case of 30 GeV eRHIC when we discuss it. What is also very interesting in this is that in reality, we have CW beam, so there is one accelerating and one decelerating beam, one accelerating, one decelerating beam at every cycle. So essentially, this is just, this beam gives energy to this beam, and it just continuous process. What is interesting is that first attempts to build such machines at Stanford and Argonne turns to be not very successful because beam became very unstable at microamp level, and it took about additional 30 years before JLab constructed first real eRHIC with 10 milliamps of average current and 100 MeV beam. Since then, of course, many people are thinking about building them, so it's 1997 they commissioned. And we also building absolutely novel R&D eRHIC at Brookhaven. This is its real schematic. This is superconducting gun, which will be capable of operating this 20 MeV superconducting LINAC, which will be capable of operating up to half amp of average current, which is about 50 times above current record at JLab. So let's remind you just on this simple cartoon what RHIC is about. RHIC is actually a very versatile collider, which has two rings, one called blue, one the yellow. Which of them can operate with different particles from polarized protons, which is unique for around the world. This is the only polarized collider in the world. And from light ions to heavy ions. And one of the things which is important that essentially any species could collide with any others, with exceptions that we didn't do so far, proton collisions with heavy ions, but this is in plans. In addition, we plan to add polarized light ions like helium-3 to study spin of neutron. So one important feature here, because it's something which is people are usually concerned, because with commissioning of IBIS now we can actually even collide uranium, and always people are concerned. This is what is the reason why RHIC operation is so expensive? Because they collide in gold or maybe radioactive uranium. Just to give you a perspective, very, very simple. So if you have a golden wedding ring, it will be enough to run RHIC continuously in gold-gold collisions for about 10 million years. So this is not really expensive adventure. In addition, total amount of uranium that we use in RHIC, it's actually less than in one speck of drywall in your house. There is also no concern about radiation. Actually, we're using not stable isotopes. So As I mentioned, RHIC dominates landscape of Brookhaven. You can see it from satellite, you can see it from airplane, and compared with it, you can see that even an SLS2 looks like a toy machine. So, and also what is important that RHIC2 era is here, and one of the advantages that it has, it's a stochastic cooling, which was invented by two Mikes, Blaskowitz and Brennan, and implemented by them. So I'm showing this just to demonstrate something which I think unique and it's happened just recently. So it's one of the advantages. This was a typical picture of luminosity in any hadron collider. As I mentioned, you can only lose particles. Your beam can be longer and fatter. So your luminosity is dropping. It's never increasing. And what was done that during this run with a three-dimensional stochastic cooling, this is a radio frequency technique, the ion beam was cooled both longitudinally and transversely, and luminosity grew. So there's no need for anybody's imagination to understand that integrated luminosity here is significantly smaller than here. So this is one of the things which RHIC does, and there's many other things which are in working, and there's many things RHIC can do as well in the future. So what RHIC was accomplished, you probably have heard many things in the press, and that the fact, this list I will not read about it because it's things which are very well known, that quark-gluon plasma was generated first time, and in my opinion, as a not nuclear physicist, the main thing that you can do is actually to disprove theory. So before RHIC was built, there was common perception that quark-gluon plasma will be just diluted gas, and it turns out to be a fluid, which is very, very unusual. And I'm pretty sure that while we study deeper and deeper nuclear matter, we will find many things, also predictions untrue, and will change our perception of life. Also, one of the things which is probably truly unbelievable, that there's a hint of the symmetry violating and QCD vacuum fluctuation, which is possible source of universe baryon asymmetry. We are living in real world where we have particles surrounding us, and we don't understand why antiparticles are not around. This is maybe one of explanation. And also there is a heaviest antimatter element was produced by RHIC. So essentially, instead of only having protons and neutrons in periodic table, now there is also anti-protons and anti-neutrons in periodic table. This is a very, very fantastic accomplishment. And of course, there is many discoveries ahead, and RHIC is in mid-strive. It's really a very productive machine, but I have to switch to something which we think will add features to this machine. But before switching it, I will try to answer interesting question, which is saying, why electron-hadron collider? And I can tell you why, because it's many of my accelerator physicist friends, they're saying, well, we understand you're going to collide protons with protons or protons with antiprotons to hadron colliders, or ions with ions, as an energy frontier. And you find something and you want to pinpoint, you will use electron-positron collisions, because you really can very, very describe this new findings. You really pinpoint details of this new particles or something like this, and why you will collide hadrons with electrons. And even so, it sounds very naive question, but actually it's not very easy to answer in 2 sentences. And the best answer I found so far is, at least for myself, that in electron-ion collider or electron-hadron collider, you have a particle with a known state, which is electron. Essentially, it's a point particle. It's elementary particle. And you have particle which is like a soup or a beef stew of quark gluons and everything else, and you collide. And in this, because you know state of initial particle, you actually can find information about hadron. In the other way, you can think about this if you have complicated distribution of from one side and complicated distribution of the other side, and you trying to find a product. Mathematically, you have to convolve, and deconvolving is a real headache. So this is why electron ion colliders are essentially allow us to measure structure of the hadron. And HERA, the world's first and only hadron collider, which was built in DSE and currently decommissioned, really demonstrated this in lepton-proton collisions. What HERA didn't have polarized protons and didn't have ions, heavy ions, and this is something which we plan to add. So one of the things which is also, if I want to really answer it on a more fundamental level, I should at least show these two diagrams, that in hadron-hadron collisions, we have complicated interaction with gluons. One electron-hadron collision there is called deep inelastic scattering, when electron exchange virtual quant with the hadrons. And this is directly connected to gluon field. But usually I'm asking my colleagues from physics department, from electron ion collider task force to explain it. And instead of this, I just will use a few slides from my colleagues from Matt Lamont and Elke Eschenauer to demonstrate their view why, for example, you need something to figure out what switch watches a bit from. This is actually Feynman, who is a very famous physicist who invented Feynman diagrams, saying essentially that colliding proton with proton is just like colliding Swiss watches, trying to figure out how they're built. And it's true, when you collide and you have enough energy, you can find melting temperature, you can find how many wheels are flowing out, and so on. But you really need X-ray flash to see where handles are, where hands are, how many stones they're built from, and so on and so forth. Essentially, you need a microscope, and electron ion collider is exactly this femtoscope, which is we're saying. So there is a list of most compelling questions. I just will not dwell too much on them. I will say that this is one related to spin physics. It turns out that there is about 30%, 60% of spin is unaccounted for proton, which is very simple stuff. There is one possibility, which is also quite incredible, that one can imagine three-dimensional imaging of the nuclear matter, nucleus or nuclei. And in addition, there can be gluon saturation. Gluon saturation, essentially, I showed this graph where at low X, there is more and more gluons. This is because they're interacting with each other and creating more and more softer gluons, but it cannot go forever. It just cannot go to infinity. And to some sense, to demonstrate this, for best demonstration, I found this. It's highway in China. So if you have, if you will try to add one additional gluon to this, they either have to collide or combine. So quantum tomography of nucleons is also one of the things which is possible or can be possible with the hadron collider. And this is something which I will not express in details, but combination of picture of the hadrons in momentum space and in coordinate space, which is possible. Combination of them essentially will provide with something which is called tomography of the nuclei. And people say, why not? Why cannot do it when we are doing this every day in hospitals? Of course, this is just a joke, but this is true that technique is somehow similar. And again, I mentioned spin puzzle already, and this is something which is also probably the most important, that RHIC, a recent RHIC result showed that there is non-zero contribution of gluons into the spin of the protons, but 60% of proton spin is still uncounted. And only 30% of spin belongs to quarks, valence quarks, which means that, and this is a question which both RHIC and eRHIC are trying to answer. In very, very simple things, we are here on the top of the iceberg, and there is a lot of things which can be answered by electron-ion collider, which we want to build. So what is eRHIC? So in addition to one of RHIC rings, we can use blue or yellow ring, depending on configuration. So all species, we plan to add polarized and polarized electrons, and if necessary polarized positrons. So one of the things, center of the mass energy is very important because it allows you essentially to reach deeper and deeper. Because this is why it's called femtoscope, because this is when you can reach deeper. And square root of S is nothing else than center mass energy. Essentially, it allows you to tell you what you can generate by doing this. One of the important features, it's extremely high luminosity of eRHIC. And just to be sure that it's understood, it's about 1,000 times above what HERA generated. So it's very, very serious. It's absolutely unprecedented level of productivity. And in addition, we will have electrons and protons with polarized, and we can switch polarization of electrons and protons on bunch-by-bunch basis, which will remove systematic errors. So I will just say a few words about history. This is a brief history of eRHIC, so I will not... Okay, I will try to stay here in this case. So it's it was followed by a white paper on a eRHIC electron-ion collider. And in 2003, DOE included eRHIC into facilities for the future sciences, 20 years outlook. So it was very nice, and we responded right away in 2004 with so-called eRHIC zero-solder design, which was based on Rin design and with just appendix describing ERL design. So it took us about 3 years of very, very deep studies to understand that actually ERL design gave us significantly higher luminosity, and it's become main option. And we also recognized that cost is a very important factor for eRHIC to be exist. So we designed a staging option for eRHIC, essentially how to build it slowly. And in 2009, we completed design of myriad, which was just exercise with a local small machine. And presently, we return to the cost-effective green, all internal and RHIC tunnel design with staging electron energy from 5 to 30 GeV. So this is how it looks like. And this is presently, it's eco-friendly because it's inside present enclosure, so we will not bother snakes or frogs or anybody else outside of RHIC tunnel, which is important. It's based on a compact magnet design at present with a small gap magnets, which is 6 passes around the machine. This allows us to keep cost low. This is just, you can see, quadruple, which you can carry in hands. And this is how it works. So it comprises polarized electron gun, pre-accelerator, which is also energy recovery Linux, 600 MeV, 2 Linux. There will be electron cooler, which I will discuss, coherent electron cooler, which I will discuss, and also beam dump, we can collide in 3 places, in location of Phoenix star or in location of new detector. And depending on configuration, we can figure it out. So what we do, we initially generate electrons, polarized electrons in the gun, and accelerate them to through the first LINAC to 600 MeV, and they come into first LINAC, where it's about 2.5 GeV acceleration process. After that, it's accelerated to, roughly speaking, 3 GeV, and it's going into one of the first array of the magnets into the arcs, and it's going around. It's going to the second LINAC, and after that, it's accelerated to, roughly speaking, to 5.5 GeV, and again, going into the top stack here. And then it's doing this 6 times around, and going through every stack of these magnets to the top energy. After that, at the top energy, it's colliding with the hadrons either in one or the other collider. And then what we do, we change phase here by 180 degrees, so it's 30 GeV, and then we energy recover everything but the last 10 MeV and drop it. So this is 3,000 times lower energy than the top energy. This is how efficient this machine is. So we can operate gigawatt level energy, reactive power of electron beam in such machine. This is a little bit more details how our LINACs are organized. This is BNL3 LINAC, which is designed for eRHIC. So there is beams at different arrays of magnets are coming through, and they're combined through the combiners, which are designed as well. And then they combine together and going through the LINAC, either accelerate or decelerate. Then they, by dipole magnet, because they have different energies, they separate it and continue their travel. So, and this is how it's specifically looking at 10 o'clock for decelerating beam. So this is, roughly speaking, everything. And again, as I remind you that there is accelerating and decelerating bunch, and accelerating and decelerating. So in this superconducting LINAC, which requires actually only 10 watt of losses will be going to helium for a 20 megawatt LINAC, which is about 1 megawatt of reactive power, which is going through for each beam. So it's a very, very effective device. There is some overhead, which I will not discuss, which is called for noise compensation. So this is how it looks. This is three-dimensional rendering of this machine. This is a full-blown LINAC here. And you can see there are teeny tiny magnets there. You just can see it because they are very small compared with the RHIC superconducting magnets. One of the things which is important is the cost. And cost is very important because it's a 30 GeV machine. It's unique. It's a energy recovery LINAC, superconducting, and so on. So we developed a very clever and simple staging strategy. We'll start with low energy from 5 to 10 GeV. It's not determined yet what it will be. And what we'll do, we'll keep energies or ratio of the energies of electron beams the same from injection to the very top energy. This is the ratios. I will not read them. Trust me, we calculated every number here. And after that, what we'll do, we'll start building up injection LINAC, energy recovery LINAC, and each and every LINAC. So we'll start from a short LINACs and we'll start adding them up. This is how staging works, and this is just a real first real eRHIC type cavity, which is was built by AES here. So I think that covers it. So I will go with you to just bear in mind. I will go through the main concepts, main elements of the concept. So we choose ARL for electrons to reach high luminosity at high energy. I will detail this in a second. We also assume that we can cool hadron beam by factor 10, both in longitudinal and transverse direction, which is very unusual and very, very tough. because neither stochastic or electron cooling can do it. So we plan to use coherent electron cooling. We take advantage of small beam sizes in RL. We decided to use small gap magnets, 5 or 10 millimeters. This is something which is still under optimization. But beam sizes in eRHIC is actually only 100 microns. We found that solution for timing, and I will not dwell here because it's a rather complicated issue, and for RHIC is the only one way to move arc when you change the energy. We took advantage of recent advance in superconducting quadrupole technology developed for LHC and designed interaction section with beta star of 5 centimeters, which is about 10 times smaller than evaporated at RHIC and 5 times smaller than in Tevatron. And following success of KKB with crab crossing, we accommodated this approach into a new interaction regional layout. And we also assume that we can generate up to 50 milliamps of polarized electrons, which is a non-trivial feat as well. And all this assumption bring top luminosity above 10 and 34 standard units, which is, as I mentioned, about 1,000 times above previous collider. And if polarized positrons are needed, we also can add it, but it will be at lower luminosity. One important feature for us was also to be not only cost conscious, but environmentally conscious. So we don't want to consume a lot of electricity. So we established for ourselves a limit by what total maximum power can be lost by electron for synchrotron radiation, for any other losses, like cavity losses for high order modes, or resistive wall losses for the vacuum chamber. So this is something which is very important. This is what brings us to the limitations that we're reaching about 10 megawatts at 20 GeV with 50 milliamps current. And above this, because synchrotron radiation losses are increasing, we have to drop current as a power to keep synchrotron radiation losses under control. So this is design luminosity. There's a complicated table, so I just will show you what is here. Essentially, luminosity is similar for different species when we calculate it per nucleon, the 20 GeV electrons. Energy of luminosity doesn't depend on energy of electrons if we go in from below 20 GeV. It will stay the same. Only above 20 GeV we have to drop it as energy of in power 4, which is give us factor 5 at 30 GeV loss in luminosity. And it's linearly scaled with proton luminosity, with hadron energy. So this is essentially things which are extremely pleasant and very, very nice. And luminosity is really determined by maximum electron beam current that we want to operate. This is just different way of presenting luminosity. This is energy of the hadrons, 250 GeV here, and this is energy of electrons. And you can see how luminosity is essentially covering. This will be phase 1 of our eRHIC machine. So it's comfortably covering all the area of interest. So I will cover now a few challenges and solutions that we found. One challenge arose when we were studying a ring-ring collider. We found that essentially luminosity was limited to few 10 and 32. So it became a electron ion collider with energy reach below Hera and luminosity comparable with Hera, which was very, very unpleasant, not very compelling case. There were additional minor problems. And so this is why we decided to use a new technology, which is called energy recovery LINAC. So it doesn't have a problem because, as I mentioned, it's very, very, very comfortable and recovery high reactive power of electron beam, gigawatt level. It's not a big problem. But the most importantly is that in ring-ring scenario, because we collide in the same beams for billions and billions of terms, you only can tickle electron beam. While here we have only single collision per pass, and you really can hammer it with a sledgehammer. And just in this case, you can really increase luminosity by up to a factor of 50. And this is just demonstrating you what's happening. So this is original electron beam, which is going like this. This is this original scenario. This is simulation by your house. So this is very small beam. When it actually propagates through the proton beam creates very nonlinear field. So you can see this is essentially turns like a galaxy. So it's a very, very strong distortion. So nobody can imagine that something like this, if you do this to electron beam during one collision, it can survive more than a few turns. So essentially, this is only possible in linear RHIC scenario. But what is important for us that doesn't matter what intensity of the proton is. What is happening that this beam stay confined. As soon as you can see that this is essentially, this is 0.2 millimeters, this is 0.2 millimeters, 200 microns. So the bottom line, we really do not, we can recover this. We take energy back and throw this beam away. This is as fundamental for eRHIC luminosity as you can imagine. So there's a lot of challenges that we have for eRHIC. This is a list from polarized electron gun, where I need to increase 10 times electron beam current. Coherent electron cooling, which is new concept. Multipass ARL, where we have to increase both current and energy. Crab crossing, which was never demonstrated for hadron colliders. Fortunately, our friends and RHIC plan to do so. And understanding of beam effects, which is a new type of collider, never was used ever anywhere. Reduction of beta star, as I mentioned. Multipass ARL, essentially it's very significant increase. Feedback for kink instability suppression, new concept. And space charge effect compensation, it's also no concept. So essentially sometimes we feel that we are climbing clouds. And fortunately, teamwork always allows us to keep our feet on the ground. Challenge 2. So I will just describe how we approach to create interaction region with beta star 5 centimeters. It's 5-fold reduction compared with Tevatron. And how to satisfy all requirements from detector folks, which is, believe me, it's not an easy fit, but we're really working very closely with task force, and it's a pleasure. This is how this design looks like. So this is where protons' trajectory is. So protons are coming out of detector. They're going through the first magnet. They're going around here and turn, and then go to existing spin rotator from RHIC. So this is their trajectory. Electrons are brought here through the very, very smooth banding with few Gauss field, because we really take advantage of 90 meters of, and because we are crossing with a 10 milliradian angle, we actually don't need to bend them in IR, so there are no synchrotron radiation from bending magnets. These are new type magnets, which I mentioned. And so, as I mentioned, we're using Crab crossing 10 milliradian. We have to use a high gradient, large aperture focusing magnets. And also we have to integrate with detector. For example, we need to integrate neutrons which will go in direction of original protons, so there will be a clear path for them. And one of the things which is a contribution from our collaborator from SMD, design of very original design of the magnet, which combines dipole and quadrupole coil, which allows us to propagate electron beams through this teeny tiny hole. So all hadron products from detector going through this hole, while electrons going where field is equal 0. So it's very, very clever and inventive design, which is typical for BNL. Of course, the same way that as a crab crossing was introduced by Bob Palmer quite a long ago. So if you have angular collision, you can see carefully here that beams actually interact very, very little, just in a little bit, so essentially not the time. But as soon as you put tail up and nose down. This is essentially the same as a head-on collision. So it's a very, very clever design, which has required so-called crab cavities. There is the original design of cavity, which was proposed by Lan Binzvi. There is currently a lattice of eRHIC, of RHIC, which allows to do this to hadron beam. Okay. Challenge number 3. It's one of the things which is really to generate 50 milliamps of polarized electron beam. So when we were talking about this, it was 1 milliamp. Fortunately, our colleagues from JLab increased beam current to 4 milliamps from a single cathode. So the entire idea is that you increase current, and suddenly your cathode just dying very, very fast. So this is a very tricky element. Nobody knows how to improve this. So one of the possibilities, which is a very old idea of mine, is to use Gatling gun principle, which is essentially a simple idea. So you have multiple cassettes. You generate electron bunches from individual cassettes. And after that, you just have a rotating electric field or magnetic field, which combines them on the axis. It's a very simple idea, but of course it takes a very talented group of scientists and engineers to really design. So there is this real design, which is currently under construction of a Gatling polarized electron gun, led by John Skaridka. And so there's 24 cassettes here. Shroud, there is a preparation vacuum chamber for gallium arsenide, which is gallium arsenide cassette, which can be delivered here. And what's happened is that electron beam will go bend, and they will be recombined in this area by rotating magnetic field. So this is something which I'm looking forward to see operational and proven. One thing which I forgot to say is that entire idea here to demonstrate that lifetime of cassettes, individual cassette, doesn't depend on the current from the other one. Otherwise, it won't work. So this is very important demonstration. Challenge number 4 that we were facing is how to cool 250 GeV proton beam at RHIC to 1/10 of the transverse and longitudinal emittances. As I mentioned, both stochastic cooling and electron beam cooling cannot do the job. Stochastic cooling can cool and actually can cool a little bit ion beam, which has about 10 and 9 ions per bunch, and rather long bunch. And cannot do it for proton beam because the proton beam has 100 times more particles. So stochastic cooling is essentially cannot work for eRHIC. This is traditional array of gigahertz bandwidth stochastic cooling. We studied electron beam cooling for RHIC-2 for quite a long time, and we learned that cooling efficiency of such machine falls at least as the square of the hadron energy, which means that at high energy is becoming very inefficient, and we really learned that it cannot do this job. So the idea was that to develop coherent electron cooling, and idea here, so let me see if it's working. Yes. So it's a very simple idea. If you, okay. Sorry. Okay, I will hold it. So it's a very simple idea if you think about this. So it's you have electron and hadron beam, you merge them, they have the same relativistic velocity, the same relativistic factor. So essentially in comoving frame, they rest with respect to each other. So it means that they have the same relativistic factor and, of course, 2,000 times different energy. So when they propagate through the modulator, each hadron, because hadron is positively charged, it will attract electrons, as I showed on this picture one more time. So this is a hadron, it attracts electrons, and they create cloud, which is called Debye screening. Many people have heard about such effect, Debye screening with Debye radius. And it means that each hadron will create an image about the same charge, but opposite sign in electron beam. It's like a little chirp much shorter than FEL wavelengths. So what then we're doing, we separate electrons and run them through the high gain FEL, which is actually working as an amplifier. So it's not saturating nothing else. So essentially, the idea is that to increase density here by about 1,000 times. So and instead of a single spec, we'll have a periodic structure, which we'll call wave packet, of low and high density, with about probably 100 or so, 50 to 100 such modulation. So this is simulation from TechX, which is modulation. This is amplification. This is actually how it's working in Kika. So this is just something which is drawn by hand for simplification. So while we're doing this with electrons, what we do with the hadrons, we are propagating them through the dispersive section. So hadrons with a high energy go faster. They have a shortcut. Hadrons with a low energy going slower, falling behind and with respect to the central energy. So what then we do here, we recombine with electrons and we use longitudinal field. Because if you think about, we'll put hadrons with central energy just on the top of the high density of electron beams, where electric field is 0. So if you have electron with a high energy, which is in front, it will be attracted to this by these electrons and will be put back. And hadron with a low energy will be behind, so it will be accelerated. So it means that we will, on average, we will reduce energy spread of hadrons. It's called cooling. This is exactly that. It's similar to stochastic cooling, but the only difference here is that we are moving from RF frequencies, which are in centimeter range, we are moving to the optical frequencies. And this is why it actually can do it. And because we are not, because it's a new principle, so of course we want to test it. And we are building an interaction point to a RHIC, a new facility, which is called coherent electron cooling proof of principle experiment, which is supported by DOE and also program development and LDRD funds, where we essentially will demonstrate cooling at 40 GeV of the hadron beam and RHIC. And challenge number 5, this is my last challenge. And the only, essentially, to keep eRHIC price tag low. And the only way, essentially, to avoid excess expenses in engineering solution, like cross-river crossing. By essentially what we're doing, we are using original cost-effective solutions. So one of them is small gap magnets, as I mentioned, and the other, which is currently in development by Dejan Trpajevich and Thomas Rosa, FFG arcs, which actually may allow to save significant amount. And of course, we are using RHIC tunnel and multi-tone aerial and many other things. So I come to my summary that RHIC, eRHIC following RHIC will open a new discovery potential for fundamental sciences. It will open a new window through which we can glaze on universe around us and actually to the matter inside us as well. And eRHIC design progressed very well. We had external review of our design, which went very successful. Cost estimate is underway on 2 cost-effective scenarios. And physics of collider is well understood. We didn't find any showstoppers, and there is extensive R&D underway. And in 5 to 7 years, we plan to have completed and to be ready for eRHIC construction. BNL has actually all experts we need to do this, which is very nice. So I would like to invite you to join us in this extraordinary journey. And to finish, I would like to acknowledge and to thank Elke, Matt, Paul, Abby, and Steve for providing slides. I also want to thank my collaborators from TechX for providing this movie and simulation of CAC. Of course, many colleagues from CAD for providing material for this talk, and also our people who fund us DOE, as well as support by program development and LDRD. And I want to thank you for your attention. Thank you. So we have a guidance from DOE that we should stay for accelerated construction under $500 million. We think we can build 5 GV energy recovery LINAC, or maybe even 10 GV FFG machine. It's still in progress. I cannot tell you final numbers. Final machine definitely will cost more. But one important feature that we want to state here is that we really have $2 billion facility, hydrogen machine, which is hydrogen machines are the most expensive. And so we're adding a less expensive part to this. And this is why we are very competitive.
This coherent electron cooling is quite important. But your test is going to be relatively late.
Well, we plan to start commissioning of coherent electron cooling in 2 years. So if you're interested, I can tell you where we are now. We have our electron gun, SRF electron gun, is under construction. We plan to start its test at production site in Michigan in this December. And in a year and a half, we plan to install 20 MeV SRF LINAC, which is LINAC itself is actually already they started building superconducting cavity. So it's aggressive plan. Nobody agrees, and it's R&D. So you always hope for the best, but prepare for real life. And funding is not always there. But so far, we are very successful.
So how much of these are the electrons and the protons gathered together? Is there a net charge? Will the imbalance of the net charge still, or is the electrons equally charged?
Where in coherent electron, there are significantly fewer electrons in hadrons. It's about probably about factor 100. Number of electrons about 1%. Because hadron beams actually have very large charges. It's like up to 100 nanocoulomb.
If there are no further questions, there should be wine and refreshments out in the lobby. And let's thank our speaker one more time.
Thank you.